We are going to be moving right along then, looking at 1.7. So 1.6 had a lot to do with kind of like how we can take more complicated functions and think about them as like simpler functions, as changes made to a simpler function. 1.7 is going to be looking at how we can, different ways that we are able to combine our functions. The good news for the first four is that they are going to follow exactly what you'd expect. I got a little bit bogged down last time by notation, so rather than showing you guys like the proper definitions, I just want to kind of keep your intuitive understanding about what's going to be going on with our first four operations. These are called pointwise operations. Y has to do with the definitions. If you want to know more, take a real analysis class when you're a senior and being a math major. But for now, we're just going to go by what we think this function would do. So I've got two functions here. I've got f of x defined as above. I've got g of x defined here. And for our first function that we are trying to find, we are trying to find f plus g of x. So what would we think that we should do? What do we think we should do to find f plus g of x? No, definitely not. This is not, yes, exactly. So we are taking our functions and adding f of x to g of x, right? But this is not distribution, because distribution would be multiplication. We're not multiplying anything. We are simply taking our function f of x, and we are adding it to our function g of x. Okay, that's why it's pointwise. We basically like treat each function like it's its own thing and then add them together. All right, we can simplify this. How can we simplify it? It's going to be 2x plus 6. The x squareds are going to cancel here. We have to do something, though, first. It's not super clear from this example why we need to do it now. We have to deal with the domain first. First, we have to, because this question is determine the domains of these functions that we are getting as well. Okay, looking at this particular function, do we ever have to worry about dividing by 0? No, I don't see any denominators. Do we have to worry about square roots? No, I don't see square roots here. And so what is our domain going to be? All real numbers, so everything from negative infinity up to infinity. Fantastic. We had to do that before we simplified, right? What we're going to see is it's not going to make a difference in this case, right? We simplify this. In this case, the x squared and this negative x squared are going to cancel, and we're going to end up with 2x plus 6. And notice, what is the domain of 2x plus 6? It's also all real numbers. Okay, so simplifying in this case did not change our domain. But again, I want to kind of hammer this in. Let's consider a hypothetical here. Let's instead think of f of x as 1 over x plus 3. And maybe g of x is equal to negative 1 over x plus 7. And I want to, again, pointwise add these functions. So I want to do f plus g of x. And so I do that. I get that this is equal to 1 over x plus 3 plus negative 1 over x plus 7. Just like before, what do I have that's going to cancel? Yeah, the 1 over x. I've got a positive 1 over x over here. I've got a negative 1 over x over here. Those are going to cancel and make 0. But what am I not allowed to plug into my function? I'm still not allowed to plug 0 into my function. Because if I try plugging 0 into my function, I'm going to get something that is undefined. I'm going to get something that does not exist. And so even though this function simplifies down to just 10, right, everything cancels, we're just left with 10, we still have to make it so that 0 is not a part of our domain. Not because there are problems with plugging 0 into 10, but if we look back to the original functions, we run into issues when we try to plug 0. Right? It's a little bit tricky. The TLDR here is if you're asked to find a domain, do it before you cancel things. Right? Don't go all striking through willy-nilly. I don't want to look at this stuff. Let's make it as simple as possible. First, check for domains. Then you can start going through and making your function look all pretty and nice. Right? We'll see this problem again when we look at functions that have holes in them. That's going to be when we look at rational functions. We will see this problem come up a little bit when we look at composition as well. There are some functions that when you do this new operation that we're going to do, they come out really nice. There are no denominators, but you run into this issue where actually, in fact, along the way, you have to exclude some values. Okay. So it's not really going to come up here, at least for a little bit. I just want to prime you to when we are checking for the domain, let's build good habits early, simplify later. Simplify at the end, check domain first. All right, let's take a step. Let's take, we'll say like 10 minutes or so to work through B, C, and D. Now, as far as domains are concerned, which one is maybe gonna throw us for a loop? Which one is maybe gonna have issues? Yeah, notice D, we've got some kind of division something or other going on. So let's work through. A lot of it is very intuitive, exactly what you'd expect, but be a little bit careful with D. Are there any values that we need to exclude? So this is the interval. So this is our domain. This is the domain, and then this is just this simplified. So I put it under here, but that's just because I already have a vertical space. So this and this are the same. What is the domain? And the domain is like all the values of x that we're allowed to plug into our function. So in this case, we're never running the risk of dividing by 0. We never run the risk of dividing by negative. So our x can be whatever we want it to. We don't have to worry about that. But if we ever have to run the worry of dividing by 0 or something sort of negative, then we want to throw those out. So. No. It's f of x times g of x. Yeah. So this is composition, which we'll look at here later. But you want to be very careful. It's f of x times g of x. Yeah. It's that pointwise multiplication. Good.
You're supposed to multiply by.
You don't have to. You can leave it unsimplified. Yeah, I do not.
So the simplification is necessary.
Yeah, you don't need to simplify for.
Okay.
Yeah, the only thing I like to simplify is take fractions and make them look a little cleaner. Yeah, do we ever have to worry about dividing by 0? No. Do we ever have to worry about taking square roots and negatives? It's all numbers. Very good. Very good. You don't have to. You can if you want to. I will not follow you if you want to, but you do not. Yeah. So think of this as like one big equation. them being multiplied together. Yeah, we'll look at composition next, which will be, it has like its own special symbol. Yeah. Double check the domain. 0. This tells me that I need to throw out when x is 0. But do I divide by 0 when x is 0? No. So we want to think, what are the values of x where I'm dividing by 0? And those are values that we want to focus on.
This domain, all these domains are still going to be on.
Yeah, because we're still not worrying about dividing by 0, still not worrying about square root of 0, square root of negative 0. Yeah. Now, D is going to be annoying because we're going to have a function of x in the domain. Yeah. So then the question is, when is that equal to 0? And we want to throw those up as well. You don't have to do out this multiplication. You can if you want to, but you do not need to. Quick thing to note, though, this is not composition, which we're going to look at here in a bit, which is what you've done, where you took g of x and plugged it in for x in f. This is multiplication. Yeah, so fg of x, a lot of people are jumping ahead and doing the next thing that we're going to do, which is composition. I'm glad that we are familiar with that and that we've seen that. That's fantastic. We'll talk about that in a second. This is pointwise multiplication. So this is f times g of x. Yeah. So it's not going to be for like a nice clean integer number, but are there like irrational numbers that we have to use that would? Yeah, it's not going to be a nice whole number. It's going to be one of those gross irrational ones. Yep, and ones. So positive root 6 and so those are the two. Okay. This all looks good. And what are we thinking for? Okay, good. Yes. And then. So thinking, what are the values of x that make that denominator 0? Those we want to throw. So you would want to set up an equation.
So the domain is going to be 0.
Does it need to be positive?
This.
Or not? So think going from negative infinity up to infinity. There's going to be, but yeah, you're the right answer. Yeah, very nice. Okay, let's take a look at this. Overall, I would say the functions look really good, and then the domain for D is what is being a little bit tricky. Is that a fair assessment? Okay. So first thing for B, I did not say anything here, but you guys did a very, very good job of this. Keeping things in the parentheses. This is x squared plus 2x minus, in parentheses, 6 minus x squared, where that negative is going to distribute and hit everything in that parentheses. So taking that negative and distributing it. And so what we end up with is 2x squared plus 2x minus 6. You could factor 2 out to the outside as well, and that would be fine. But you can leave it like this, and honestly, also you could leave it like this, and that's fine. However you like. For f times g of x squared plus 2x times 6 minus x squared. If you wanted to write out this multiplication, that's fine. You would do a Punnett square, and that's great. And I'm not going to do that here, but you could, and that is your own prerogative if you would like to. I am perfectly happy with you leaving it like this. All right, and then lastly, f divided by g of x. This is x squared plus 2x over 6 minus x squared. Now we said that our domain for b and c, it's going to match. It's going to be all real numbers. There are no denominators. There are no square roots. We don't need to worry about anything. Where are we going to need to worry for d? Yeah, we want to know when is this denominator equal to 0. In other words, we could say that we need to make sure that 6 minus x squared is not 0. Is that a fair way to write that? Okay. We could solve what we have here for x. So adding an x squared to both sides, we get that x squared cannot be 6. Taking the square root of both sides. Remember, when we take a square root, we get a positive version and a negative version of our values here. So I get that x squared is not allowed to be 6, and that tells me that x is not allowed to be plus or minus the square root of 6. So not a particularly nice, clean number. This one is irrational, but that's okay. We're just going to leave it like that. I am excluding those values. And so what is my domain going to look like? It's going to be everything from negative infinity up until this negative root 6. We want everything in between these two. And we want everything from positive root 6 up to infinity. So the only values that we are throwing out here are negative root 6 and positive root 6. You would. This is just your final answer. In fact, not only would you not, there isn't a way to simplify this. That is as simplified as it's going to be. Now, there is a temptation to do what here to simplify? Cancel the x squareds. You can only cancel with division if what you are canceling is multiplication. All right. So the fact that I have an x squared added into my numerator and an x squared added or subtracted from my denominator means that I can't cancel them with division. In fact, there's really no way to get at this x squared over here. That's just going to sit there. So very, very, very important. Those x squareds would not cancel. This would be your final answer. All right. Questions with our pointwise operations here? All right. Those ones are nice. They follow pretty much what you'd expect. I didn't even define them for you, and you guys were able to just figure out how it would look, which is great. So these are fairly nice and clean. We are also going to be introducing a new operation. So we've done addition, subtraction, multiplication, division before. Go figure, it translates to about exactly what we'd expect. Our new operation, though, this is going to be something entirely different. I saw a couple of people starting on this with f times g of x, so we're just going to clarify kind of what that is going to look like. And I will verbalize, so on like a test or a quiz, if I want you to do a pointwise operation, like this pointwise multiplication, I will tell you you're doing multiplication, right? This is pointwise multiplication. This is not composition. Okay, so what is composition of functions? I think a nice way to think about composed functions, this is like a function whose input is another function. Right? So we're taking a function, plugging it into another function. Oftentimes, this is written in our function notation. So if you have felt really, really good with our function notation, this is going to continue to be just exactly what it is read to be. So for instance, we might see something written like f of g of x, where what is this telling us to do? Not multiply. So everywhere we see an x in our function f, we replace it, we substitute in this g of x. Right? So not multiplication. This is substitution. This is composition, brand new kind of function. Yeah, g of x would go instead. Exactly. All right. Another way that you will sometimes see this written, this is sometimes written with like this little open dot, f of g of x. That's fine. I just want you to know that this can then be written as this. My first step when I see something like this is I just rewrite it like this, because this tells you exactly what to do, right? Our function notation tells us very, very clearly what are we doing. We are substituting x for another function. You guys have actually already done this before. We didn't call it that when we did, but when we were told that like f of x is equal to x squared plus 2x, and I want to know what f of x plus h is, what did we do? Well, we took x and we replaced it with a different function. We replaced it with x plus h. And this became x plus h squared plus 2 times x plus h, right? It's the exact same thing that we did before. Now, granted, the functions that we are going to compose are a little bit more complicated than things like x plus h, but the core idea of taking x and replacing it with a different function is still there. That's still kind of the penultimate idea that we're working with. Let's take a look at an example here. So looking at example 2, we are trying to evaluate f of g of 2. So remembering, what is this asking me to do? Well, this is saying, well, everywhere we see an x in our function f, we are replacing it with g of 2. Let's do literally that. So this is f of, I'm going to write this as g of 2. Everywhere we see an x, we replace it with a g of 2. This is going to be equal to, our f is defined up there. This is going to be g of 2 squared plus 2 times g of 2. Okay. So that's kind of as simple as it is. Like that really is kind of it. But we can do a little bit better than this. how would I figure out what g of 2 is? Yeah, substitute in 2 for g of x. So for instance, we can say, well, I know that g of 2 is going to be equal to, well, this is going to be like 6 minus 2 squared. 2 squared is 4. This is also, okay, ends up being equal to 2. Okay, so what does that tell me? Well, that tells me that everywhere I see g of 2, I can replace it with what? 2. So those are the same. I could interchange them all I want. This is going to be equal to 2. So now our f of g of 2 equal to, I'm going to say equal to f of 2 now. Which is equal to 2 squared plus 2 times 2. And so what do I get as my final answer? This is 8. 4 plus 4. Okay. Things I don't like about this example are the fact that g of 2 is equal to 2. I think that can be a little bit confusing. I want to make very clear the reason why we ended up plugging 2 into our outermost function, into that f, is not because of the 2 here. It's because of the 2 over here. So the fact that g of 2 was equal to 2 is why ultimately we plugged 2 into our function. All right. There are faster ways to do this. Probably finding what g of 2 was at the start would have been a nice quick way to do it. But I'm just trying to show you, like, here is what I would say a very fail-safe, just very like, this is telling me to do exactly this. This is telling me to do exactly this. And so writing that out to just kind of make the steps a little bit more clear. Do you have any questions with this first example here? All right, let's try another. Looking at B, what am I being asked to do? Yeah, so we're taking f of whatever this is, this z plus 1, f of z plus 1, whatever that is, plugging it in for x in my function g. Okay, so what is this going to look like? Well, it's going to look like 6 minus, and then instead of x, what do I have? Well, I have whatever this is, this f of z plus 1 nonsense. F of z plus 1 all squared. Okay, so at a very face value glance, that's all we're doing. It could almost be done, but can't actually be done here. Let's actually write out a little bit more as to what this is. How would I find f of z plus 1? What is this going to be equal to? Exactly. So we're taking all of our x values from f, replacing them with z plus 1. And so what do we end up with here? This is going to be, I'm going to kind of do what I did above. This is z plus 1 squared plus 2 times z plus 1. So just taking x, replacing it with z plus 1. And that's exactly what I'm looking for. This right here is now going to go in for what I see here. Okay, it's going to look a little messy. That's okay. I don't require us to simplify, and I will continue to not require us to simplify. So we're okay with a little bit messy. What is this going to look like? Well, this is equal to 6 minus, we'll say in parentheses, this is z plus 1 squared plus 2 times z plus 1. And what do we do with that? That is squared. Okay, a little bit gross looking. Again, I don't require us to simplify. Let's leave it gross. That's fine. That's a lot of the work right there, just kind of cut out. But we are just taking f of z plus 1, replacing it with what we know that is. How are we feeling with B? Pretty good? No idea? All right, I will again take the silence as extreme proficiency and mastery over this material. One more then. This one's going to feel a little bit weird, but all we're going to do is follow what the notation tells us to do. Yeah. Yeah. So in this case, we are looking at C here. This is using that operator, this kind of like open little bubble here. And exactly as Haddon has indicated, this can be written. And in fact, what I would do first is I would rewrite this as f of x. So what does this tell us to do? Yeah, we're taking f of x, and everywhere we see an x, we're replacing it with f of x. All right, let's see what that's going to give us. That is going to become f of x squared plus 2 times f of x. All right, that's great, but we can do better. We know what f of x is. F of x is just what we have up here. Awesome. So we replace what we see, and what do we end up with? This is going to be x squared plus 2x all squared plus 2 times x squared plus 2x. Which again, looks weird, but it's just, you don't have to simplify it, and it is just following what the notation tells you to do. You take f of x, and you replace all of the x's with f of x. Yeah. All right, any questions with composition? No questions? We feel good? We don't have any pieces of this that we'd like to go over when we look at the steps? We're like, oh, of course, this is obviously what we're doing. Nothing to clarify. This looks sensible. Y'all look crazy. All right. We got about 10 minutes left. You guys are more than welcome to use the rest of this time to work on the My Math Lab work. The 1.6 problems. So you should be able to do like the first half of the work because we are now done with 1.6 and 1.7. The 1.6 problems are what I'm going to look at for that extra bonus point. So have that done tomorrow. And then it'll be 1.7 the next day, 1.8 the day after. And then the assignment as a whole is due Sunday. So ideally, have it done in class by Friday, but if you need extra time, do Sunday. And then what do we have on Monday? I don't know if I mentioned this last class, but does anyone know? Nope. A test on Monday. Unit 1 test. So covering covering everything that we've done until now. Right. We will have a review day, a full review day on Friday, where we'll look at some of these topics. We'll talk about that a little bit more as it gets closer. Yeah. I mean, I could do that, but the alternative would be like starting Unit 2 in order to do that. And I don't really want to, I like to test and then start the next unit. Yeah. Yeah, so for the classwork, you'll still submit your supporting work. For the extra point, you no longer need to submit your supporting work as you go. You can just submit your supporting work at the very end. Yeah, so you don't need to do it like incrementally anymore. You just do it all very end. And there are plenty of questions that are graphing questions. You don't need supporting work for anything like graphing questions. Yes. Are you staying during tutoring?
No, I was just asking, like, are we going to come back?
Oh, yeah. I will get that back to you guys. I can do it today. I can do it now.
And also, so no quiz on 1.6 and 1.9.
Yes, we'll probably focus on that during the review. But yeah, there isn't a quiz in between. Graphing questions. Okay, couple of things. Actually, so we still have a couple of people who haven't taken the quiz. So I can't go over like particulars, but just some kind of common things. A lot of it was just like not including justifications when I asked for a justification. So making sure that we are reading through. Domains, that's just a thing that we're kind of going to need to practice. Getting very used to that. One of the big things on number 4 that I saw a lot was if I am asking you to determine an interval over which something is happening, what kind of values am I asking? If I'm asking for pieces of our domain. So those are always going to be X values that I'm looking for. I saw a lot of people giving Y values there. I gave partial credit for that. Realistically, that was maybe a little bit generous. But just kind of keep in mind, if you are talking about an interval over which something is like increasing or positive or negative or decreasing or whatever, generally speaking, those intervals that we are talking about refer to X values. The other kind of piece, this is more of, again, not something that I really counted off for, but still something that I wanted to address. A lot of people said for the max, that the max was the point, infinity, infinity, or negative infinity, infinity. I did not count off for this, but this is wrong. This is not a point on graph. Very specifically, infinity is a symbol that we use to describe the idea that we go on and on and on and on and on forever. So I get what you mean. That's what you're trying to communicate here. But there's not like there's some biggest number infinity that will eventually hit, and that's where our graph will cap out. Instead, we would say that the max does not exist. Yeah. Or is that where you're asking? How we would say it. Yeah. So instead, you would just say that there is no max. The max does not exist. Fantastic. Domain stuff. People did pretty well with the functions, and then a little bit of the labeling as well, kind of throwing people for a loop. I would go back over some of those notes because that is going to show up on the test for sure. I'll definitely give you some numbers for you to determine what kind of numbers we're looking at. All right. If you have any specific questions from the quiz, like why something was wrong or why I graded in a certain way, you can come up and, well, here, but I can keep going. It's for both. Your idea of why you want to get your function logic isn't wrong, but it's because this has a yeah. So when we're talking about we're going to say like this is work from increasing. Yeah, so it's from exactly. So I didn't know what kind of point. Yeah, so it's from yeah, so that idea that you just communicated, it's starting from here onward.
Oh,
so from 0. So you normally say like from 0 to.
So I would do both of those?
Yeah.
I remember there was something like you can't say it's the same thing twice. Like, oh, it's the absolute and relative. You can't have them at the same.
No, you can't. You can't have the same.
You can't have one min being also.
Yeah, you can't have a min and a max. This is incorrect. Our function is decreasing over that interval. It's because you're starting at 0 and then letting your mind you're branching off in both directions. We start to the left and work our way forward.
Yeah, I realize it's just after that. And why the plus 2?